Welcome to another Explainer. Today, we're doing a 5-minute technical deep dive into a really fascinating computational fluid dynamics study. We are going to unpack a rigorous mathematical investigation of blood flow through narrowing arteries, modeling the exact hemodynamics of what happens when dangerous plaques build up on our arterial walls. It's this perfect, fascinating blend of biology and high-level engineering. But before we get into the heavy math, you know our guiding philosophy here, right? Computational fluid dynamics is 99% convergence errors and 1% magic. Our goal today is to strip away those errors and show you the absolute magic of a properly configured simulation. Here's our roadmap for today. First, the physics of arterial stenosis. Second, pre-processing, looking at geometry and meshing. Third, the solver setup. Fourth, analyzing the hemodynamic results. And finally, the quantitative data. All right, Section 1. The physics of arterial stenosis. So the absolute bedrock of our entire simulation rests upon the Navier-Stokes and continuity equations. Think about it. The continuity equation basically says that the mass entering a control volume has to equal the mass exiting it. When an artery narrows, the flow area decreases. So to keep that mass constant, the math literally dictates that the blood has to accelerate to compensate for that reduced lumen diameter. For this specific 2D, steady-state, laminar flow model, we're keeping things a bit streamlined to simplify the complex nature of human blood. We're treating it as an incompressible Newtonian fluid. We lock in a density of 1,060 kilograms per cubic meter and a dynamic viscosity of 0.0035 pascal seconds. This gives us a really solid baseline that mimics actual physiological properties. Moving right along to Section 2, pre-processing, where we tackle geometry and meshing. This is such a great look at our pre-processing phase in ANSYS Design Modeler. We are comparing the bare geometry of a severe 70% stenosis, which is basically a highly constricted artery, to our finalized structured quadrilateral grid. Notice how beautifully that mesh elegantly conforms right to the narrowing throat. That's crucial because we absolutely need to capture the complex flow behavior exactly where it matters most. Now, any good engineer knows you can't just pick a mesh size and hope for the best. You have to prove it mathematically. In our grid-independent study, we tested 0.5, 0.3, and 0.2 millimeter grids. The winner? The 0.3 millimeter medium mesh. With over 20,000 nodes, it was selected because it perfectly balances computational cost with rigorous accuracy. It grabs all those essential flow features without totally nuking our processing power. Next up, Section 3. The solver setup in ANSYS Fluent. So we need our setup to mirror human biology. We drive a steady 0.2 meters per second inlet velocity against a 0 pascal gauge pressure right at the outlet. And crucially, the artery walls are boarded by standard no-slip boundary conditions. Simply put, that means the fluid velocity right up against the wall surface is exactly 0. Okay, this right here is the proof in the pudding, convergence. In CFD, your results mean nothing if the math hasn't settled. But look at this. You can clearly see the x and y velocity residuals dropping safely below our required 10 to the negative 3 threshold. The continuity residual stabilizes super smoothly too. That validates our numerical stability and gives us the green light to actually trust the data. All right, the fun part. Section 4, analyzing our hemodynamic results. Check out the stark contrast in these velocity contours. We've got a healthy artery cruising along with a gentle, uniform maximum velocity of 0.3 meters per second. But then, look at the severe 70% stenosis. Boom! We get this massive localized spike up to 0.71 meters per second. The flow area has shrunk so violently that the blood literally has to squeeze through that throat at more than double the speed just to conserve mass. Now, shifting over to the pressure contours, notice how the upstream pressure just dramatically builds up in that 70% case. See that deep red zone? That happens because the blood requires a massive amount of extramechanical force to push through the stricture. A healthy artery barely resists the flow, right? But a stenosed one? It acts like a dam, forcing the heart to work exponentially harder. And that brings us to wall shear stress. which is the frictional force the flowing blood exerts tangentially right on the artery wall itself. Look at the intense, concentrated stress at the throat of that 70% stenosis model. The extreme velocity gradients near the wall are creating intense shear forces. And this isn't just an engineering curiosity. High wall shear stress is an absolutely vital metric for medical professionals predicting endothelial damage and future plaque progression. To truly visualize the physical chaos happening downstream, these streamline plots are just incredible. They perfectly capture the smooth, uniform, laminar flow of the healthy vessel. Contrast that with the severe downstream flow distortion, recirculation zones, and flow separation caused by the 70% blockage. It's a turbulent mess that further disrupts healthy blood delivery. Finally, let's look at the hard numbers in Section 5, quantitative data. This table perfectly synthesizes our entire deep dive today. Just track the progression here. At 30% and 50% occlusion, the metrics definitely rise, but they stay relatively manageable. But look at what happens when that artery hits 70% occlusion. We see a truly catastrophic jump in the pressure drop, soaring to 143.28 pascals, alongside a maximum wall shear stress of 14.80 pascals. The resistance to blood flow doesn't just increase, it becomes severe and completely nonlinear at this critical threshold. So we've successfully proven the fundamental mechanics using steady-state Newtonian assumptions and captured the essential hemodynamic features of arterial stenosis. But I want to leave you with this to ponder as we wrap up today's explainer. How dramatically would these velocity spikes and shear stress metrics shift if we modeled the complex, non-Newtonian thickness of actual blood, driven by a true pulsing heartbeat? Because honestly, that's where CFD goes from 2D engineering to true patient-specific magic. Thanks for joining me on this explainer, and as always, keep iterating.